Alright, for some reason I was cut off doing 1110, so I'm gonna call them part 1 and part 2. I already did part 1, so part 2 is right here, 1110. So I was left off showing you the Maclaurin series for cosine, and I showed you all the basic ones are on page 804 in table 1. So example 3 represent the sine function by Taylor series. All the ones on page 408 are Maclaurin series, so Taylor series centered at anything other than 0, at in this case pi over 3. Okay, so we have sine x Maclaurin series on page 408. That's different. That's Taylor series at c equals pi over 3. So we know that f of x, so this is a solution. Taylor series can be written as n equals 0 to infinity the nth derivative at pi over 3 over n factorial x minus pi over 3 to the n. So we're going to find the function and its derivatives at pi over 3. F of x is sine x. F of pi over 3 is root 3 over 2. F prime of x is cosine x. F prime at pi over 3 is 1/2. Cosine pi over 3 is 1/2. We're looking for a pattern. Negative sine x. The second derivative at pi over 3 is negative sine pi over 3, which is negative root 3 over 2. The third derivative of negative sine is negative cosine. So the third derivative at pi over 3 is negative 1/2. The fourth derivative of cosine is negative. So now we can see the pattern. Okay, so you're getting sine and then you're going to get cosine. The fourth derivative at pi over 3 is root 3 over 2, and then you're going to get 1/2 and so on. Okay, a pattern. Okay, so now the Taylor series for that function at c equals pi over 3 for sine function is sine x. F of pi over 3 is root 3 over 2. F prime is 1/2 x minus pi over 3. F double prime is negative root 3 over 2 divided by 2 factorial x minus 3 pi over 3 square, and then f triple prime, which is negative 1/2, so over 3 factorial x minus pi over 3 cube, and so on. And that was page 93. There is no page 94, so I jumped from 93 to 95. Don't look for page 94. There's none. Okay, just a mistake. So now we can find a Taylor or Maclaurin series. Okay, but the question is, does this series converge? And if it does it converge to the original function? So that's what's gonna lead us to that. Convergence of Taylor series, Taylor and Maclaurin. Okay, because Maclaurin is a special case of Taylor series. If f is differentiable of order n, so if f exists, f prime, f double prime, fm plus 1 exists. Okay, so you can differentiate to at least the n plus first power. Let me write it down. If f is differentiable of order n plus 1 in an interval I containing c, containing some number c, then there exists a letter z between x and c, that's mean value theorem, such that f of x equals f of c plus f prime of c x minus c, the Taylor series, f the prime of c over 2 factorial x minus c squared plus the nth derivative at c over n factorial x minus c to the n plus what we call the remainder Rn of x. This is basically the sequence of partial sums. Instead of Sn of x, we use here Tn of x. Okay, sequence of partial sums. And the remainder. And we know if the sequence of partial sums converges, so does the series. Okay, so now if the limit that I was talking about, n goes to infinity, Rn of x equals 0 for all x in I, then the Taylor series for f converges. Not only does it converge, it converges to f of x itself. Means f of x does equal the series that we're talking about. Fn at c over n factorial. So we need to show that the remainder goes to 0. Okay, and just left out is Rn of x. It's the n plus 1 derivative at z over n plus 1 factorial x minus c to the n plus 1. Okay. And the proof is there. You can look at it. So let's go to example 4. In example 2, we derived Maclaurin series for f of x equals, so from example 2, actually it's on page 804, table 1, we have that, but I did it in example 2. We had cosine x is 1 minus x squared over 2 factorial, x4 over 4 factorial, x6 over 6 factorial, which is sum from n equals 0 to infinity, negative 1 n over 2n factorial x to the 2n. So we proved that in example 2. The question is, can we prove that the series does converge to cosine x? Okay, so in order to show that, we need to show that Rn of x, so we need to show Rn of x goes to 0 as n goes to infinity. Rn of x is fn plus 1 at z, where z is between c and x. C is 0 in this case, over n plus 1 factorial x to the n. X to the n plus 1. Remember, there is no c, c is 0. Okay, remember that if you do the derivative of cosine, it's either sine or cosine. It's either sine x or cosine x, plus or minus. When you do absolute value, it's less or equal to 1. Sine or cosine is between negative 1 and 1. So if you're doing absolute value of Rn of x, it's absolute value of n plus 1 z over n plus 1 factorial x to the n plus 1, which is less or, that's a 1, less or equal to 1, so xn plus 1 over n plus 1 factorial, which we know it goes to 0 as n goes to infinity. Why? Because I have it down, so if that goes to 0, then the series converge to that function. And here's why. Because we did sigma x n over n factorial converges by the ratio test, so the limit of the nth term is also 0. If the series converges, then the limit of its nth term is 0. So not only did we prove that the series converges, we proved it converges to cosine x. So what are the, now I'm on page 98, what are the guidelines for finding a Taylor or Maclaurin series? You know, the steps that I've been doing. I've been finding f of x and all of its derivatives and try to find a pattern. Then use the sequence looked in step 1 to form the Taylor coefficients. We plug those in. And then with this interval, we can determine whether or not the series converges to f of x. Only this third step, only if they ask you to do that, okay? Only if they ask you to do that. Alright, page 99, find the Maclaurin series, meaning C is 0, okay, whenever they say that C is 0 for g of x equals e to the negative 3x, give its radius of convergence. So we're gonna go to page 408, table. We're gonna get the help of e to the x. E to the x is 1 plus over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, sum x to the n over n factorial, n equals 0 to infinity, and it converges from negative infinity to infinity, okay? So e to the negative 3x is 1 plus negative 3x over 1, negative 3 squared over 2 factorial, 3x cubed over 3 factorial, which is sum from n equals 0 to infinity, negative 3 to the n, x to the n over n factorial. Negative 3x is between negative infinity, and so x is between negative infinity and infinity. Alright, so now how do we find again Maclaurin series for h of x equals x cosine x? Well, we know the Maclaurin series for cosine x, right? Cosine is 1 minus x squared over 2 factorial plus x4 over 4 factorial minus x6 over 6 factorial, and so on, with sum negative 1 to the n, x to the 2n over 2n factorial from 0 to infinity. All we have to do to get h of x is times everything by x. Okay, so the x minus x cubed over 2 factorial plus x5 over 4 factorial minus x7 over 6 factorial plus x9 over 8 factorial, which is sum from 0 to infinity, negative 1 to the n over 2n factorial. X times x to the 2n is x to the 2n plus 1. Straightforward, okay? So now binomial series in college algebra, we go over binomial expansion of 1 plus x to the n, where n is greater or equal to 0. Here, we're going to look for binomial expansion into a series for any n or k, any k. So find the Maclaurin series for f of x equals 1 plus x to the k, and determine its radius of convergence. But k doesn't have to be, the only thing that k doesn't have to is 0. Okay, k could be anything. So again, to write it as Maclaurin series, c is 0, so we're going to write f of x equals 1 plus x to the k. So f of 0 is 1. F prime of x is k using the power rule, k minus 1. F prime at 0 is k times 1 is k. F double prime at x is k, k minus 1. 1 plus x to the k minus 2. F double prime at 0 is k, k minus 1. So you can see second derivative, k minus, this is basically 2 minus 1. Now let's look at the third derivative. It's k, k minus 1, k minus 2, 1 plus x, k minus 3. So this is k minus 3 minus 1. That means f triple prime at 0 is k, k minus 1, k minus 2. and so on. So the nth derivative at x is going to be k minus 1, k minus 2, and where do we stop? K minus 3 minus 1, so it's k minus n minus 1, which is actually k minus plus 1. F nth derivative at 0 equals k minus 1, k minus 2, blah blah blah, k minus n plus 1. Now we can write the series since we have all the derivatives. So 1 plus x to the k is f of 0, which is 1, f prime of 0, x, which is kx, and then k minus 1 over 2 factorial x squared, k minus 1, k minus 2, x cubed over 3 factorial, plus k minus 1, k minus 2, k minus n plus 1 over n factorial x to the n, and so on. And if you do the ratio test to get the radius of convergence, the limit as n goes to infinity, an plus 1 over an, you do this, n plus 1, and then over an you get 1. That means the radius is 1. That means it converges over between negative 1 and 1 to some function. In order to show it converges to 1 plus x to the k, then we have to find Rn of x and make it 0. Okay, so based on this, find the power series. Find the power series for f of x equals cube root of 1 plus x. That's E because this would be 1 plus x to the 1/3. So all we have to do is plug 1/3 in for k. So instead of 1 plus kx, it would be 1 plus 1/3 x. And then minus 2x squared over 3 squared times 2 plus 2 times 5 over 3 squared, 3 factorial x cubed minus 2 times 5 times 8. You can figure that out. X to the 4, and it converges between negative 1 and 1. That's why I said we're not going to do 1111, so I took some of 1111 and embedded it in 1110 because they're the same, kind of. So find the first 3 non-zero terms in the Maclaurin series e to the x tangent inverse x. So basically we're going to multiply power series, multiplication of power series, because we have both of these series. We have e to the x and tangent inverse of x from page 804. E to the x is 1 plus x squared over 2 factorial, x cubed over 3 factorial, and then tangent inverse x is x minus x cubed over 3 plus x5 over 5 minus x7 over 7. So to times them, so 1 plus x squared over 2 plus x cubed over 6 plus x4 over 24, and then x minus x cubed over 3 plus x5 over 5. So we take x times it by all that. X times 1 is x times x is x squared, x cubed over 2, x4 over 6, x5 over 24, and then this times all these. But we only need the first 3 terms. Negative x cubed, we line up like terms. Negative x4 over 3, negative x5 over 6, negative x6 over 18, and so on, and then x5 over 5 times 1, x5, so it's x6, but we don't need that. So anyway, so this will come down, this will come down. Excuse me, x cubed over 2 minus x plus x cubed. That's all they're asking for, but if you want to do more, x4 over 6, because I did it, 3 over 40 x5. Okay, simple multiplication and addition of polynomials. Same thing with division. Of power series. So find the first 3 non-zero terms and the Maclaurin series for tangent x. So we have Maclaurin series for sine, we have Maclaurin series for cosine, so we're going to do long division. Sine is x minus x cubed over 3 factorial, x5 over 5 factorial, and then cosine is 1 minus x squared over 2 factorial, and so on. So if you do long division, you will get the answer x minus x cubed over 6 plus x5 over 120, and then 1 minus x squared over 2 plus x4 over 24. So x over 1 is x times 1 is x times negative x squared over 2 is negative x cubed over 2, x times x4 is x5 over 24. If you subtract, change the signs. So you get negative x cubed over 6 plus x cubed over 2 is going to be x cubed over 3, and add these guys, you get minus 1 over 30 x to the 5. Do that again, x cubed over 3 divided by 1 is x cubed over 3 times 1. X cubed over 3, that's negative x 5 over 6. And minus plus, so you get 2 over 15 x to the 5, 2 over 15, and you don't need to do any more. This is the answer. And one last one is about estimate. 64. Could you imagine evaluating sine of x4 using what we know? You can't, I mean, it's not going to work. Neither use substitution, nor basic stuff, nor addition by parts will work on this one. Okay, so evaluate 4 decimal places. So we're going to do power series. So we know that sine x is x minus x cubed over 3 factorial, x5 over 5 factorial, x7 over 7 factorial. So sine of x to the 4, we plug x to the 4 for all the x's. So it's x to the 4 minus x to the 4 cubed plus x to the 4 to the 5th, which is x to the 20, x to the 4 to the 7, x to the 28 over 7 factorial. And if you want to integrate, it's all of all these guys between 0 and 1, which would be x to the 5 over 5 minus x to the 13 over 13 times 3 factorial, x to the 21 over 21 times 5 factorial, x to the 29 over 29 times 7 factorial, between 0 and 1. You plug the 1 in there, you get 1 over 5 minus 1 over 13 times 3 factorial times 5 factorial, 29 times 7 factorial, and so on. You plug the 0, you're going to get zeros. If you do all these, you get roughly 0.1876, and that gives me the estimate that I'm looking for. And that's it for 11, 10 and 11, 11, and we're done with the class in terms of lecturing.